In this video, we will walk through neuron activity and interneuron communication. Neurons exist in one of three states: polarized, depolarized, or at equilibrium. The distribution of ions inside and outside the cell creates voltage differences that determine which of these states the cell is in. Think of it like Kool-Aid mixing in water. When you first pour the packet in, it is highly concentrated in one spot, yet it naturally mixes with the water until it is evenly distributed across the pitcher. This represents a state of equilibrium, and is similar to how ions seek equilibrium across the cell membrane. When a cell is polarized, there are more negative ions inside the cell, and reaching equilibrium would mean moving towards a more positive state. When a cell is depolarized, however, the concentration of positive ions inside the cell is greater, and the opposite is true. At rest, a higher number of negative ions inside the cell creates a resting membrane potential of about negative 70 millivolts. In this state, the cell's negative charge creates a potential for change via external forces. In neurons, these forces include the electrical gradient, which deals with the attraction of oppositely charged ions, and the concentration gradient, which deals with ion flow from high to low concentrations to reach equilibrium. For membrane potential changes to occur, ions must be able to move across the cell membrane, and this is where ion channels come in. Ion channels can be activated in one of three ways. First, ligand-gated channels open in response to specific chemicals binding to them, much like a lock is needed to open a door. Voltage-gated channels open in response to voltage changes in the cell's membrane potential. Finally, mechanically gated channels open as a result of physical distortion of the cell's membrane forcing them open. These different forms of gating allow our nervous system to process a wide range of information and respond appropriately to different situations and stimuli. Ion pumps are also important, as they help restore resting potential by moving ions in and out of the cell, ensuring the neuron is ready to fire again. An action potential is a rapid change in voltage that occurs in a cell's membrane. When ion flow raises the cell from its negative 70 millivolt resting potential to its threshold at negative 55 millivolts, the cell rapidly depolarizes until it reaches about 40 millivolts, triggering an action potential. This is an all-or-nothing response. If the negative 55 millivolt threshold is not reached, nothing happens. After firing, the neuron undergoes repolarization until it enters the refractory period, where it temporarily becomes more negative than negative 70 millivolts. During this period of about 1 millisecond, it is extremely difficult to get the neuron to refire. Eventually, the neuron returns to its resting state and is excitable once again. The action potential is then transmitted down the neuron's axon, repeatedly regenerating until it reaches the synapse. Some neurons are myelinated, meaning they have a fatty layer covering the axon. This allows for more rapid saltatory conduction, since action potentials need only regenerate at the nodes of Ranvier, rather than all along the cell's axon as they do in unmyelinated neurons. When the signal reaches the axon terminal, it must cross the synaptic cleft to reach the next neuron and continue information propagation. There are two types of synapses: electrical and chemical. Electrical synapses are designed for rapid, synchronized communication. In these synapses, presynaptic and postsynaptic cells are extremely close to one another, allowing for direct ion flow between cells. Chemical synapses use neurotransmitters to relay signals and are critical for adaptive behaviors, as their structure and function can be changed if needed. These synapses are what allow for plasticity and adaptation to our environment. All chemical synapses share a common structural plan, with each one having a presynaptic terminal, a synaptic cleft, and a postsynaptic region with ligand-gated receptors. When the action potential arrives at the axon terminal, the influx of sodium creates a voltage change that triggers the opening of voltage-gated calcium channels. Calcium flows into the axon terminal and binds to synaptic vesicles, which are small membrane-bound structures filled with neurotransmitter. This binding action pulls the synaptic vesicles downwards towards the synapse, where they then fuse with the cell membrane, releasing neurotransmitter into the synaptic cleft, a process called exocytosis. Neurotransmitter then binds to postsynaptic receptors, either ionotropic receptors in which neurotransmitter binds directly to ion channels and allows ion flow, or metabotropic receptors, in which neurotransmitter, rather than directly triggering the opening of the channel, activates second messengers, or G proteins, that float over to the ion channel and cause it to open. Sodium ions floating in the synaptic cleft are then able to flow through these open ion channels, generating action potential in the dendrite of the postsynaptic neuron that can then start the process again. Of course, neurotransmitter cannot remain in the synaptic cleft indefinitely, so it must be removed or destroyed somehow. This happens in a few different ways. First, there's enzymatic deactivation, in which enzymes are released that break down neurotransmitters into fundamental pieces that can be recycled. Next, there are presynaptic reuptake transporters, which act like vacuum cleaners, reabsorbing neurotransmitter back into the presynaptic cell for reuse. And finally, there are glial reuptake transporters, which take neurotransmitter into glial cells where they can then be broken down and recycled. Returning to our postsynaptic cell, we must note that not all generated currents are identical. In fact, neurotransmitter binding actually leads to two possible responses. First, excitatory postsynaptic potentials, or EPSPs, occur when sodium influx creates an increased positive charge, making action potential more likely. Inhibitory postsynaptic potentials, or IPSPs, on the other hand, occur when chloride influx increases the negative charge of the cell, making action potential less likely. Neurons receive thousands of EPSPs and IPSPs, which are combined over space and time. If the summation of these synaptic inputs results in enough EPSPs to reach the firing threshold, an action potential is triggered. Thus, we see that it is not the result of one or even a few neuronal signals, but rather it is the simultaneous firing of large groups of neurons that allow action potential to propagate along neural pathways. Neural conduction is a cyclical process, with voltage changes in one group of neurons influencing what happens in the surrounding neurons. And it is this cyclical and synchronized communication between neurons that causes the transmission of information throughout our nervous system, resulting in the behavior we see. Thanks for watching.